Welcome to Lesson 7.8, Sufficient Conditions for Parallelograms. So basically everything in this lesson can be basically summarized into this box. So this box will be your main resource, your main look back, your main tool for most questions, and for basically assessing whether or not a quadrilateral is a parallelogram. So the sufficient conditions basically just mean if one of these conditions are met, then we have a parallelogram. So we have four different conditions that we are looking at. Sufficient condition A: if in a quadrilateral, one pair of sides is both parallel and congruent, then we have a parallelogram. So one pair of sides needs to be both parallel and congruent. In condition B, both pairs of opposite sides are congruent, then we have a parallelogram. So both pairs of opposite sides are congruent. In C, the diagonals bisect each other, meaning that they are broken into two congruent pieces for each. And then sufficient condition D is if both pairs of opposite angles are congruent. So the pair here and the pair here. So if we meet any of those four conditions, then that quadrilateral is a parallelogram. So example 1 says, is the figure a parallelogram based on the given information? If so, give a justification of why it's a parallelogram. So in this case, our justification would be stating sufficient condition A, B, C, or D. If it doesn't meet any of those four conditions, then we cannot classify it as a parallelogram. So our first image here, we see the bisectors are two congruent pieces each. So in that case, yes, it's a parallelogram. From condition C, the diagonals bisect each other. In our second image, we have congruent sides and then a different set of parallel sides. That's not enough information to classify it as a parallelogram. In our third image, our opposite pairs of angles are congruent. So yes, it's a parallelogram from condition D. In our fourth image, our opposite sides are congruent and a set of opposite angles are congruent, but that is not enough information for one of our sufficient conditions. And same with our final image. We were given two different angle measures and no other information, so that also does not satisfy one of our conditions. Example 2 mentions 2 yardsticks and 2 meter sticks are joined end to end to form a quadrilateral. What types of quadrilaterals could they form? So based on the information we were given, we know we have 2 yardsticks and 2 meter sticks that form quadrilaterals. So that tells me we have two sets of congruent sides. It doesn't tell us how they have to be arranged. So we can think about any quadrilateral that meets the condition of two sets of congruent sides. So that leaves us with three options based on their definitions. We could have a rectangle, we could have a parallelogram, or we could have a kite. And if we look at a hierarchy of quadrilaterals, all three of these share that condition of two sets of congruent sides. And our final example for the notes today is a proof based on parallelogram. So what they told us was quadrilateral QAD, where x equals the measure of angle DQU, is equal to the measure of the measure of angle DAU, and y, which equals the measure of QDA, is equal to the measure of QUA. So in other words, y is the angle here and here, and x is the angle here and here. Now, when we look at their proof, the only explanation that I really have for them not starting with the given information is, as I noted there, the book likes to break the rules. So again, you should take the given info, start your proof with that as your first conclusion, and your first justification is the given. Now, we again always want to look at the prove statement. QAD is a parallelogram, so we know our final conclusion or our final goal is to prove QAD is a parallelogram. So they filled in the conclusions for us. We just had to fill in justifications. So the quadrilateral sum theorem tells us that the four angles of a quadrilateral add to 360 degrees. So that's our first conclusion. The four angles added equal 360. Then what we call combining like terms, which technically is a commutative and distributive property, but I'd be fine if you just call it combine like terms. We have 2x plus 2y equals 360. Then we can divide everything by 2 using the multiplication property of equality, giving us x plus y equals 180. Then step 4, y plus the measure of angle QUS is 180 because they're a linear pair. That's the linear pair theorem. Then we can use the transitive property of equality to replace the 180 with the x plus y from step 3. And then in step 6, the measure of angle QUS equals x comes from them subtracting y from each side, which is technically the addition property of equality with adding a negative y. And then using alternate interior angles, angle Q and angle QUS, we can state line QD is parallel to UA, or side QD is parallel to side UA. And then using corresponding angles, angle A and angle QUS, we can state side QU is parallel to DA. Now that we've established the two sets of parallel sides, we can say QAD is a parallelogram based on the definition of a parallelogram.